Mhm. Hello, everyone. And today we have a very interesting lecture. It is about constructing a riskless portfolio. Previously in our lecture, you remember that we set a very great goal, and it was modeling the dynamic of a national market. And we assume that the financial market consists of at least three elements. The first element, riskless asset modeling, and it's clear, it is just this formula where we remember that R, it is the rate of return is constant on always and doesn't depend on operation depositing or borrowing. So this R is called risk-free interest rate. After that, we modeled stock prices. For this, we choose the Brownian motion like a basic process, and after that we construct geometrical Brownian motion like transformation of the Brownian motion with strength and with volatility. This process is a particle case of eta processes. Yes, or we can call it diffusion processes, where the coefficient function before the t, or multiplier before the t, it is like product a constant mu and market price st, and this coefficient, it is like product volatility by market prices function. Okay. After that, we needed to know how to solve this stochastical equation, differential equation, and okay, and we obtained the solution like st equals s0 multiplied e to the power, and no, you remember what is it. So it was for risky asset. And the third element, it is the derivative. And for us, we choose the European option. And for European option, on the last lecture, we obtained the formula for fair price, this call option. We derived this formula from modern perspective at like a discounted mathematical expectation of the Pio function. Yes, you remember. And this formula is called Black-Scholes formula, you know, and it's believed that it is the most important, the most remarkable model formula in both finance and economics theory. But what is value of this Black-Scholes model? What we know? We know that we have check if the value of the call option is overrated or underrated. For this, it's possible. Okay, maybe I will show you again. So we go to the NASDAQ. After that, we choose the company. What company do you want to take a look? Tesla, Google. Okay, maybe Tesla, because it,
Yes.
uh, uh, because
Yes,
it's
let's try that. Yes.
I don't hear you, Lina.
Sorry. Yes, I said let's try Tesla.
Okay, Tesla, because it's interesting, and we don't know. Tesla, because there are two Tesla. Okay, maybe this. Okay. What we see, it is about stock, one day, but it's interesting, maybe 1 year. Yes, 1 year. And what we can see that it was that the price went up from November. Yes, was election in United States, and we know it's Trump. So it was it was by January, but after that the price started to go down. Yes, but now it's something go up again. Um, and so you see that the stock prices are very fluctuated, and to trade by stocks are very risky. So for this we can use option, call option, and put option. But now example about call option. So if today the price 276, and for example we can choose the April 4, 276, and approximately this 277. Yes, the call price 11.2. You see that if the price, if the strike price less than today, so the price for call option is more. Yes, is more, and this price decrease and strike increase. Yes. Okay, so for example, we have 277, 277, and the call price for today 11.20. And the question is if it is prices overrated or underrated. For the answering, we can to use the Black-Scholes formula and obtain theoretical value, because this value, it's market value. It is like balance between demand and supply. Yes, it's like balance. But what is about theoretical price? For computing a theoretical price, we can use Median, um, Median, and it is the initial price. Initial price is 276, 276. 276, and strike price 277. It is the interest rate. It's approximately now is constant 5% for 1 year. And what is amount of day from today to April 4, working day. Today 28, it is Friday. After that, day off, and after that, can you compute?
5? No,
Five. Yes, okay, maybe 5.
no,
It doesn't
Monday.
matter. No,
Okay.
okay, 5.
It's
5.
from Friday to Friday.
So it's 5, and I don't know volatility, but I can compute it. For this, I need to have historical data. After that, to make from this logarithmic returns, and after that, to compute variance and multiply it by 252. Yes, but no, maybe 25. We don't know, but okay. So. The call price, yes, it's right, 2.75. Maybe something wrong is wrong. Maybe I need again. No, okay, 275. But if I change volatility, for example, 30, because I don't know. So it is 3.39. And what we can see on the Nasdaq 277, 277. It's like 11, yes, like 11. Okay, maybe volatility is more in for real data, yes, for real data.
I think it can be because we saw that the price changed really.
Yes, very intensively.
Yes.
So maybe no, it's interesting, but we are not going now to compute the volatility from historical data. Yes, so no, we can just no, for example, 40, maybe 40. No, even not 40. Okay. So, what we can conclude from this situation, it is that the call price is that European call option for this data, for this strike, is over-evaluated. Yes, and it means that we don't advise to buy this call option. Yes, do you agree?
Yes.
Yes. So it's clear. Okay, so on this example, I showed you how we can how we can apply the Black-Scholes formula for real data and what we can conclude. But it's not like main benefit of this formula. The main benefit of this model is to possibility to hedge the option. What is hedge? It is the process action to eliminate the risk, reduce the risk, yes, by buying or selling the underlying asset in a specific way. Okay? And it's called dynamic hedging. And today I'm going to show you how we can to construct this riskless portfolio. And exactly in such way, Black-Scholes obtained their formula, not like we on the previous lecture, but exactly how will be showed on this lecture. Okay, so we need to repeat, to refresh the facts from previous lecture. It is about iter lemma. So if we have iter process and we have non-random function g with these properties. So the differential from this g will be in this form. Okay, you remember it is just lemma eta, and okay. So now we are going to derive the Black-Scholes formula, how it had done by Black and Scholes. So we have ST, the price of the stock, as 0. It is the stock price at the initial moment, and we denote like S without up. At that time, we measure in years, and let f from st the price of derivative, because it is a function, yes, and this function depends on stock, on initial price and time to maturity. Okay. So for stock price, we have geometrical Brownian motion. It's Formula 1. Formula 1, maybe slideshow, yes. It's Formula 1. And for derivative prices, yes, because derivative price is changing every day too. It is a random process. We can use the lemma eta for function s. So f, it is price of derivatives. If it is it's a maturity time, so we know that it is like maximum between 0 and s minus k, yes. But at any other moment, it's not this formula like maximum. It is like function f from s and t. And since it is f from s at t, we can apply lemma eta and write the derivative df. So now we have two formula. First, it is a stochastic differential equation for stock prices, and second, it is this stochastic differential equation, and we can say that it's process eta, but for derivative price. Okay. And first step, we rewrite the equation 1 and 2 in discrete form. It means that instead ds we write delta s, instead dt delta t, and instead dz delta z. Yes, just this. And two formula we rewrite in like equation form. So we have equations 3 and 4. It is for stocks and it's for derivative. After that, we need to introduce a definition of portfolio, of investor portfolio. What is this? Investor portfolio at theta. It's simple. It's just simple vector. And this vector contains n coordinate, and each coordinate means how much we take into this portfolio stock, no, not stock. How can I say that? Not only stock, it can be stock or derivative, and how it's called one by one word. Assets. Oh, okay. So really, Really, I need just to have a look. Yes, different assets. After that, we can compute the value of portfolio. Value of portfolio. For example, if we have portfolio theta 1, theta 2, and P1 and P2, it is today's prices for these two assets. So the value of portfolio we can compute like sum of products. Yes? Understand? Yes? Maybe.
Yes.
Yes.
Yes, it's not. No, okay. For example, we have three Google assets and two Tesla assets. And today price for Google 520, for Tesla 217. So we find product and sum, and it is the value of portfolio for today. Okay? Okay. Mhm. Now we consider a certain portfolio. Maybe I need to explain. Okay, when we take a look into formula 3 and 4, we can see that the random component in this formula, it is just delta z. Yes, delta z. This and this. And without this delta z, it was ordinary equations. Yes. So the idea is we would like to construct portfolio. For this, we need to multiply this by something factor, this by something factor, and to add or to subtract. What can you propose? What can you propose? Multiply to this, and find, for example, sum, and a reason is don't have the term with delta z in result. So you see that this common part, yes, this common part. So what you can suggest, Elena?
Maybe subtract.
Okay, if we subtract from this, but what can I do with this? No, it's not 0. This minus this, yes? But I would
Yes.
but what I need to do? Feder. It's easy, really. If I subtract from this, so it will be this minus this, and it's not 0. But can I do something that it will be 0? No, we have multiplied, for example, left and right side by something, and after that add or subtract. We can our aim to don't have the term with delta z.
Like multiply by df ds and then
Yes. Yes, we multiply the equation 3 by df ds, respect to ds, yes, and after that subtract, or multiplied by minus, and after that to find sum, yes. So it will be this df ds multiplied this, and okay, and as a result it will be delta s plus delta f equals this plus this, yes.
Yeah.
And this multiplied. No. We multiplied left side.
The whole
No,
equation,
yes,
yes.
but the idea is understandable. Yes. Okay.
Yes.
So so. Points. Uh-huh. Mm-hmm. So it is this idea. This idea, it is like construct the portfolio with theta minus 1 and theta 1 and theta 2 df multiplied ds. It is instead subtract, yes, minus 1, minus 1. And we have the next portfolio, minus f plus um, df ds multiplied s. Okay, minus f, mhm, it is this, yes, and plus df ds delta s. It is like portfolio, but you see that in our case we have not S and F, but delta S and delta F, yes? So over the time period, the total profit or loss from changing in the values of the holding is. So if we constructed this portfolio in the form 5, so the changes of this portfolio will be in the form 6, yes? In the form 6. And we need to remember that delta, that delta z was this, but it is now we don't have this delta z because minus delta f it is this. So this we just multiplied by the f respect to the s, as Elena said, yes, and we subtract, so okay, and we can do it. We can do it. Delta p equals minus delta f plus minus delta. Oh, sorry. Minus delta f it is with minus, but this we multiplied by the FDS. So we don't have this term with delta z, but we have this multiplied the dfds, so we have substitute 3 and 4 into expression 6. No, it is just subtract, yes. We have equation 7. So delta z term has vanished. It was our game. After that, we can state that the rate of return on the portfolio must be equal to the rate of return of any other riskless instrument. It is because we need two opportunities for arbitrage, because in other cases will be an opportunity for arbitrage. So we assuming that the changing of this portfolio is proportion R and P capital and delta T. So we assumed that risk-free rate of return is R, and over this time period we have delta P like this. No, it's ordinary, yes, it's understandable. And after that we need to substitute 7 in 8. 5 and 7 into expression 8. 5 it is this, and not 5, 6. 6 it is this. So we need instead delta p write this, and instead p write this. And no, we can substitute. Maybe maybe it is a question we have in the test to substitute 5 and 7 into expression 8. And we have the next equation. No, because it's easy, it's technical to substitute, yes. After that we crossed this and this, delta t, and we have we arrive at celebrated Black-Scholes partial differential equation. Yes, this, we have this, we have this, we move on the left side, and it is we remained on the right side. So we have this equation, and we need to solve this equation, and to apply the initial conditional, and to obtain at the end the Black-Scholes formula, which we already know. Okay. Okay. For solving this equation, recall that PDE about the boundary condition. So what is this? It is price of derivative, and if t little equals t capital, it means it is the t capital time of maturity. So the payoff function at the time of maturity will be maximum between s minus k, between this difference and 0. No, it means if s more than k, so f equals s minus k. But other ways it is 0. Yes, you remember. For put option, the situation is opposite. Yes, remember this.
Yes.
Yes.
Okay. So we need to write this equation, which we obtained, when we were constructing the riskless portfolio. Yes, and we obtained this equation, and we can rewrite these derivatives like f. Like in this form, f hat, not hat, but I don't know, flash, f flash, and sub t, and all this. So we rewrite this equation, and let the f from TES, it is like conditional like not initial, boundary conditional, because it is t, it is time to maturity, so it's constant. So at this moment it is like function h from s, but it is no payoff function. It is h, it is in the case of call option, it is maximum between s minus k and 0. Okay. first we recognize that it's Euler equation, which can be transformed into diffusion equation by introducing the change of variable transformation. So we input this change of variable transformation. It is y equals logarithm s, and h from s, it is s h from, what is s from this? From this s, it is e to the power y, yes? And we introduce town like time to maturity. Yes, it is time of maturity minus calendar time. It is like time to maturity. So the price of derivative, which was from t and s, we can rewrite like something new function g. Okay, like some new function g from new variables town and y, and we would like to rewrite all this equation in new variables. For this we need to find derivatives, first derivatives respect to t, first derivatives respect to s, and the second derivatives respect to s2. Yes. So the first derivatives df respect to dt, it is like chain rule, because f it is g, which depends on town, but town depends on t. So it will be dg derivatives respect to the town multiplied the town multiplied the town respect to dt, yes. And the town respect to dt, it is -1, and it's why you see this like minus, yes, this. Okay. So df respect to ds, it is dg to dy, and y, it is ln s. So dy multiplied dy respect to ds, or dy respect to ds. And what is derivatives from logarithm s? It is, Feder, what is this? Derivatives from logarithm.
Exponential function.
Yeah, derivatives of ln x. No, it will be Feder.
1 divided
1 divided by x.
by f.
Да.
By
1
x,
divided by x. Exactly. Thank you. So this, it will be 1 divided by s. Yes, you see. 1 divided by s. Okay. And now we need to obtain, to compute the second derivatives from this, respect to s. And what do you think? Why we have this like two terms? Can you understand how it was computed?
Not really.
Not really. Okay. So, okay. It is because now we need to find derivatives from this. From this. Yes, because it's first derivatives and we would like to find the second derivatives. This, yes? But this is product. It is first multiplier, it is second multiplier. Yes, it's product. Do you remember how to find derivatives from product? No, if we have x multiplied y and we need to find derivatives. Do you remember this formula?
It's y multiplied by
Just derivatives from the first multiplied second.
yes, and then plus
Uh-huh. Plus x.
multiplied by y derivative from y. Oh, from y. Yeah.
Yes, exactly. It is this formula. And it is this like and plus this. Okay, so if we find the derivatives from this from the first multiplier, it will be the second derivatives, but it is and no chain rule because it is complex function and multiplied by 1 divided by s and multiplied this
But y is
like y, okay?
s.
Okay, so it is one, yes. This it is the first multiplier without changing multiplied by derivatives from this, and it is with minus, Okay,
Yes, sorry, but I don't understand why is it in the first term 1 divided by s square, not just s?
okay, because multiplied derivatives from first, derivatives from first, the g. It will be no second derivatives multiplied by 1 divided by s. Okay, because it
Yes.
is a complex function, and multiplied to this second like this y.
Ah, okay,
Uh-huh.
yes, right. Okay.
Uh-huh.
Thank you.
Okay. Um, okay, so now we have all this, yes, all this, and we need substitute this in this equation, So maybe I can write it this. Okay. Um, uh, Derivatives this respect to t, it is derivatives this respect to town equals minus it's 2, yes, 2 sigma square s square, and the second derivatives it is no, okay, maybe I will be write this in short form. it's first minus, and this, you see that it's crossed, this, and this, yes? Minus R S, and the first derivatives, it is G multiplied 1 divided by S. It is this, yes, and plus R multiplied G. And this, it is crossed too. And it's with minus, because these derivatives, it is with minus, yes? With minus. So if we substituted all of this, we have the next equation, and we can multiply both sides by -1, and it will be G, it is G, no, Y, it is G equals 1 divided by 2 sigma square, sigma square multiplied G, the second derivatives, by respect to Y, and plus, because this multiplied to this multiplied to this, it will be minus, because we multiplied by -1. Okay, it's minus 1 divided by 2 sigma square, and G first derivatives. Okay, so we have this equation, and minus R, and minus R G, and plus, and minus RG. No, okay, it's technical, it is understandable. Okay, and we can see this equation on the next slide. What it is, just all this, and after that we can rewrite this if we input this, if we denote like A, B, C, it is minus R, it is C, but this, it is like common coefficient, and in the bracket will be B, yes, B. So we have equation 11. It is our Black-Scholes equation, but only in other function G, not F, but G. Okay, and what is our goal now? Now we would like to write this equation in this form, that on the left side we have the first derivatives by one variable, and the second, it is the second derivative by other variable with some coefficient, and to find this coefficient from all these parameters what are given. And okay, maybe I don't know, but we have this course, the equation of physical mathematics, yes, all mathematical physics.
Yes.
Yes, and maybe you do something like this, no? No, this equation, maybe you know how it's called, no?
We did something like this, but honestly, I don't remember because it was in
Uh-huh.
baccalaureate.
Okay. Because was
2
I don't
years ago.
because again.
It was 2 years ago.
It was 2 years ago
In baccalaureate, yeah.
on the bachelor program, but
Yes.
not now, yes? But
Yes.
not now. What subject we have with Чернига?
Yes, we had some also this in master's program. We also had it's like a continuation. It was.
Uh-huh. Okay, okay. No, it's interesting for me to have a look for these courses on the bachelor program and on the master program. Okay, but it's called a heating equation, рівняння теплопроводності, теплопровідності. Yes, maybe you remember.
Yes, yes, yes.
Mhm. Okay, so what we need for this? We apply the next change of variable transformation in this form, and now we need to compute compute first derivatives respect to town and the second derivatives respect to y. Okay, so the first derivatives respect to town, it is the product again, yes, this and this. So the derivatives from this respect to town, it will be e, no, to the power what we have, plus derivatives of this no, of this power respect to town, and it will be alpha, yes, it will be alpha, so we can alpha. So derivatives from this multiplied new plus the second or the first multiplier alpha town plus multiply these derivatives down. Yes. Okay. After that, we need to find the u derivatives from u respect to y. Maybe I have all this. No, I need to have a look. Yes, yes, I have this. The first derivatives, the first derivatives respect to y, and the second derivatives. And if we found the second derivatives, so from this, from the first term, it will be a b square and plus and y, and that's all. But if we found the derivatives from the second term, it will be sum, because it is because it's product. Because it's product of two multiplier, and the first multiplier depends on y, and the second multiplier depends on y. So it will be it will be two terms. So it is the result of this. And after that, then we need to substitute in this equation. First derivatives respect to town, and the second derivatives respect to y. And okay, I can explain. It is the first derivatives respect to town. It is this, yes, and we need to write this equals this multiplied lambda. Okay, it is this equation, and we can see that we cross all this, and all this we cross, and what we have, lambda b square nu, it is this, alpha от alpha nu, it is this, 2 lambda beta, it is this, and what we have, new the derivative, the first derivatives respect to town, it is this, and okay, and it's all, yes, 1 2 3 4. It is 2 beta lambda. Okay, so we substitute in expression 12. It was the first derivatives equals lambda this, so we have this. Okay, well, I understand that all this it's like technical transformation, but okay. Anyway, I need to show you. So substitute, and if we compare with 11, this compare with 11 with this, yes, so it is first derivatives, it is the second derivatives respect to y, the first derivatives respect to y, and this. So if we compare what we obtained and 11, we can denote this this factor, this multipliers a, b, and c. So we denote this like a, this like b, and this like c, okay, and we see this in the next slide. So it is lambda, it is a, 2 lambda beta, it is b, and it is c. Okay, so we have our equation in this form, and it is lambda, but lambda equals a. But what is a? But a equals half multiplied sigma square. So we rewrite this equation like in 12, and instead lambda we write a, but a equals half sigma square. So so we transformed the initial Black-Scholes stochastic differential equation in the heating equation with this initial conditional, where h it is the Pio function at the it is like maximum s between s minus k and 0. And from the course of mathematical physics, we know that the solution of this Cauchy problem is in this form, and just we need only to change to replace the function h like maximum s minus chi and 0. And what is e to the power y? It is y is ln s, so e to the power ln s, it is just s. It is just s. And okay, so we have the solution in this form. Okay, and we need only replace h. But if we replace this by a function, by your function, it will be like at previous lessons, at previous lecture. It is the function is maximum between the s at the time to maturity and k. And instead maximum, we write that it's integral not from minus continually plus to plus, but from some no, from some minus d2. And after that, it is all similar, and we can write this formula. Okay, so if h, it is like s minus k, but from this d1, so we have this, the difference of these two integrals, and you can see that it is function f and from d1, but it's function f from d2, and we have this formula. Because it is the same formula, only Black-Scholes obtained this formula constructing a riskless portfolio. But on the last years, we obtained this formula using a modern perspective. Okay, but if we would like to have the fair price for put option, you just use put call parity. And that's all. And you remember how we can compute the fair price according of call option according to this formula, and we know how we can apply Python. So that's all. And in conclusion, we can say that this celebrated, very remarkable model gives a theoretical estimate of the price of European style options, and we can compare with the market price, which is a balance between demand and supply, and we can make a decision if the market price or overrated or underrated. And the second benefits of this model, it is in follow. This model shows how to hedge the option. It means how to construct a riskless portfolio by buying and selling the underlying asset. No, to eliminate risk. The reason is eliminate risk. So you remember that we apply this portfolio, but now we don't know how we can to use it in practical way. What is df respect to ds? How we can compute this? But it is the material for the next lecture, and at the next lecture you will know that these derivatives, it is just function cumulative function for normal distribution from d1. So in this case, it will be very easy to construct a riskless portfolio, and we will show this on the next lesson. No, and its reference and its end. Okay. Okay. Have you any questions?
No.
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 Okay. So we will meet at the 3 p.m. Yes.
Yeah. Okay.
Yes. See you. See you.
Yeah.
Bye.
See you.